There's more value in the connections outside of these talks than actually listening to the talks themselves. We've spoken to a lot of very experienced, very tenured people who have lots of, great stories and mistakes that we can learn from so that we don't have to make them as well.
Thank you, everybody, for coming to my talk today. Exceptionally bad, the story on the misuse of exceptions and how to do better. Now, I gave this talk at CPP Now, and they rebranded it to Exceptions in C++, Better Design Through Analysis of Real-World Usage, which I think is a decent, if not quite as catchy a title. Okay? So, who am I? Who is this guy up on stage that dares to talk about something like exceptions in C++? Well, I started using C++ professionally in 1991, so a little over 30 years ago. Back then, we did not have a standard, we did not have exceptions, and we did not even have a native C++ compiler. We had a transpiler into C. So it's a long time ago. My professional career has been mainly as a systems analysis and architect. I did 21 years as a consultant. That just means I've seen a lot of different companies and a lot of different ways of doing it right and wrong. And the last decade or so, I've been in Bloomberg, and currently I am a ticker plant engineering lead responsible for migrating from what we call Big Iron to the Linux platform, all the machines that take this massive amount of data that comes into Bloomberg for exchanges, and we push out through the terminal. So that's who I am. So what do I do when I do talks? I like to do talks on practical software engineering, and that means that it's based in the real world, where I generally do my stuff. And you can take something away. It's not very theoretic, where you go, that's great, and let me do everything I always did before. Maybe there's something you take away and use on Monday morning when you go back to work. So I have slide numbers in the bottom right. So if you come up later to give me a question, please have a slide number in your head so I don't have to root around. And let's talk where we'll be going, because error handling is an important part of what we do in the language, and exceptions sit at the beginning, or in the center of all of this, and there's a lot of controversy about it, right? So this talk will be about exceptions as seen in C++. We may talk about Python or a camel, but it will be mainly C++. We're going to look at the history of exceptions, the original goals, what were the ideals, what were we trying to get out of it. We're going to look at the mechanics of throw-catch, because if you don't know the mechanics, it's going to be hard to make value judgments about what's going on. And we're going to look at exceptions in both their use and exception class design as seen in real code. All right, that's the practical aspect. And hopefully that will lead us to better thinking on the handling of errors and also better thinking on the design of exception classes. All right, now, it's early in the morning. Everybody's probably, just booting up. But I got to give a warning. This may be a controversial talk, all right? I am probably going to cheese off the pro and anti-exception crowd equally, because that's what I'm trying to do, all right? So things to note about exceptions in C++. I think an insight you need to hold in your head, and this is what drives this talk, is that there is no exception class attribute or keyword. There's no word of power that imbues an exception class with some special properties. All right? And secondly, there is no formal definition of what an exception class is or what characteristics denote an exception class. By that I mean behavior or functionality. It's whatever you want it to be, and the only thing that really tells you it's an exception is someone puts the word exception in the class name. All right? So I say, and I'm going to go through and prove it, hopefully, usage is the primary characteristics of exceptions, so you have to see how they're being used to make a judgment on what they should be doing. So let's go and look at the exception ideals when the exceptions were going to be brought into the language. What were they meant to give us? Well, this is something I pulled out of the Design and Evolution by Bjarne, and here's what was going on when they were bringing exceptions into the language. So the following ideals were proposed. One, it would have type-safe transmission of arbitrary amounts of information from a throw point to a handler. All right, no casting of void pointers like you have on callbacks and stuff. So straightforward way of transmitting data. Second, there would be no added cost in time or space for code that does not throw an exception. Now, we did not meet that criteria because we either give up time or space or both when we throw exceptions. Third, a guarantee that every exception raised is caught by an appropriate handler. We didn't get that either, right? If something escapes the code, it takes it down. There's no guarantee that you have a handler for it. It's one of the boogeymen of having an exception. A way of grouping exceptions so that an exception that's raised, we're throwing tons of all very fine-grained exceptions. We can take them as a group. We use polymorphic exception handling. And a mechanism that will by default work in multi-threaded, meaning if you throw in one thread, it stays in one thread, all right? And then number 6 was important, especially in the early days where we were very linked in with C. Like I said, we used to have a transpiler, not a native C++ compiler. A mechanism that allows cooperation with other languages. So you could have a C++ piece of code throw an exception that was called by a piece of C or Fortran code, that was called by a C++ piece of code that has the handler in it. So how to be able to translate and move through other languages. And 7 and 8 don't really mean anything, right? So, and it says there, you know, most of these were gotten. I mean, somewhat. But times have changed. We've moved on. We've become maybe more evolved in our thinking. What does exceptions now give us? It gives us an easy-to-read happy path. All right? There's a lack of clutter in the code. There is only a lack of clutter in the code if there's a lack of try-catch in your code. All right? Lots of try-catch statements are worse clutter, probably, than what you would have instead. It decouples error reporting from error handling. Yes, we have that. Exceptions can't be passively ignored. All right, so you say with return codes, you can ignore them. You can't ignore an exception. You actually can ignore an exception, right? If you've ever done it, what does it do? Takes your code down, right? Takes your application down. So you can't ignore it. You just pay a real heavy price. And we have a simpler way for handling constructor and operator errors. So when you do a class constructor, you can't change what's coming back and say it's got something like an error in it. You have to give it back an exact signature. So this is a better way of handling constructor and operator errors. And it is the modern and recommended way of error handling in the language, endorsed by studlib, by the C++ guidelines, right? Every authority says this is the way to do it, apart maybe from the programmers who use it, right? So how does that go? We have a piece of code here, and first I have a function that returns a return code. And you see we have a function signature where we have an in-out method, maybe not the best. And then down here, we have what's called a clutter. So if we create the class, for instance, with a blank name or an age that's 0 or minus, that would be an error. And we have to remember to ask the class, are you valid or not? And if you're not, here we exit. And then we apply some function to the class, and we say, are you still good? All right, so this is the old, not so good way. So what do we do when we use exceptions? Well, the first thing you notice is I've made a function signature change. All right, it's not void, it's not returning a status. Did I have to change that function signature? No, I didn't have to. But if I left it there, I'd be probably a bad developer because it's really misleading when an error code is coming back and I throw an exception that's not really seen. All right, so, and my point here is that a lot of time when you're using exceptions, you have to know at the throw site and the call site and the context in between, right? I have to make a break and change. So here we have the happy path, right? Clean, no clutter. It's only a happy path when you look in between the try-catch block, right? Outside of that, it's kind of ugly. But inside of the try-catch block, it's really quite neat. If the class has stuff it doesn't like, it's going to throw an exception. If the apply goes wrong, it throws an exception, and all my error handling is located in the catch block. So this is, you know, kind of nice. Here's the error handling. What's the problem with this code? Anyone? All right, you see this is in main. What's the problem with this code? All right, if I have an exception that's not in my status, it's going to take my code down. All right, and in many systems, and certainly where I work in Bloomberg, I'm not allowed to just have applications go dead because an exception got out of a piece of code or someone added a new exception. I have to add one of these, an exception swallower. And what is an exception swallower? It just tells you, look, out there somewhere we had an exception. I don't know what it is. I don't know who threw it. I don't know where it came from. but it's there. It's like a shark in the water, all right? And we say, well, let's see if we can just say there's something going on in our error message, and we go on to the next piece. All right, so exceptional ideals, you usually need exception swallowers in the code, usually at main, and if you have an exception-happy throwing crew of programmers, you need them all over your code base. So let's get to exceptional definitions. What is an exception? Surprisingly tricky to nail down. Most people use a circular reference. It's for stuff that's exceptional. What is an exception? It's when it's really exceptional. All right, so it doesn't really tell you much. So I'm going to attack the problem from a couple of different ways. One is the mechanism or the behavior of exceptions when we handle them. And that's something that gets thrown, and then something that gets caught. Is an unhandled exception a bug in the code? Yes? No? Don't care? I just put an exception swallower and I sleep good at night? Okay. All right. I think it is, but that's me. So let's talk about how exceptions work really briefly in case you're not familiar with them. So what happens when we're throwing exceptions? Well, from the standard, the memory for the exception object is allocated in an unspecified way. Right? That means no matter what you're creating, even if it's an int, you have to allocate some space on the heap, which is expensive. All right? And it's outside of the regular return mechanism that you have with regular functions. You need a separate stack unwinding mechanism. You don't use the regular stack return that we have when we return from functions. We need a completely separate mechanism. And that's expensive as well. There's two types. There's a frame-based, which means as we're going through code and entering functions, we're keeping a list of all the objects that would need to be destructed if we come out of it. All right, so you pay in that thing, you pay if you don't throw an exception. And the other one is table-based, which means at compile time, I can figure out for some range of the instruction pointer what objects need to be deleted. Or, sorry, the destructors and stuff fired on them. And that you do not pay for if you don't throw in exceptions. In time, you pay for space, you get more code bloat. That's why you have to enable exceptions in your code. So what about catching exceptions? Well, an exception handler can only catch from a point previously traversed by your execution. So you can't throw it sideways or throw it someplace else you've never been. All right, it's got to go back someplace you've already been. We do polymorphic catching of exceptions with RTTI. The standard does not say you have to use it, but it's a convenient way of doing it. I'm not aware of any other way it's been done. And we have exception hierarchies, right? These are long chains typically with multiple inheritance. So what your code has to do when it hits an exception or gets an exception thrown is look for a block and sees that block. Let me go through the whole inheritance chain to find that, is this able to catch? No? Okay, let me go to the now enclosing block, check if that can do it. So that's expensive as well. All right. And then in the standard, the implementation would then deallocate the memory when we come to the end of the catch block for the object, and that's done in an unspecified way. But we have to deallocate memory that we've used. If we didn't use it, the deallocation would be cheap, but this is expensive, right? So has anyone noticed anything about our mechanism in C++? A recurring theme? Expensive, right? So look, it's expensive, it's wrote all over it, right? No, that doesn't mean never use it. I mean, if you have to pay a large bill, you want to pay it only occasionally, all right? Or I guess if you have time, you know, you're not performance, so it's kind of you're rich in time. You can throw them willy-nilly, it doesn't matter, but it is expensive and you need to know that. Let's talk about if an exception is thrown. If it's done during stack unwinding, in other words, from the throw before it hits a handler, right, your program is terminated. And that usually happens if you throw an exception while creating your exception object as it's being copied, or where you have a destructor that leaks an exception. That's going to cause stud terminate. Right? Otherwise, it can be caught by a matching handler, and then the exception is no longer in flight. It's not uncaught. And if no matching handler is found, as I said before, it will call stud terminate. And anything that goes wrong with the exception mechanism, there's no exception mechanism for the exception mechanism other than termination. All right, and terminate is in the standard implementation defined, meaning you're not going to get a rollback, you're just going to get stud abort, right? So if you're expecting something in your database flag to be taken out on an unhandled exception, it's not going to happen. Now, let's talk about exception hygiene. right? How do we use exceptions in a way that's not going to cause problems? Well, we throw by value, right? Because if you throw by reference, the stack disappears. It's an invalid reference. If you throw by raw pointers, you shouldn't be using raw pointers anyway. Go to some other talk here about that. So you throw by value. It's a copy. And when you catch it by reference. If you catch it by copy, you can get object slicing if you catch it by a base class. So you catch it by reference. And if you want to say I'm not doing anything, you can show your intent by putting const reference. It doesn't actually matter because it's a copy. And you rethrow it using no arguments. If you get catch exception E, and then you say throw E, you actually create a new exception as a copy, and now you allocate more memory. So again, not the way to do it. And the other thing is catch handlers are activated in the order they're presented. So the first one that's listed is the first one that's checked, then the second, then the third. And what that means is a base class should not go before a derived class because it would never get called. Right, so here we are, 50 layers down in the stack. I'm in some kind of panic mode and I just go, throw that exception. Boom, grenade, right? I'm rocketing up the stack. I'm laying waste to objects left and right, all right? Memory's going everywhere. It would be chaos, right? And that's why I believe at the beginning when we were talking about exceptions, there was a lot of debate of whether they needed garbage collection to handle that kind of thing, all right? But it was decided we can do it a different way. So we have this idea of exception safety, meaning we give some sort of guarantees so we can safely use exceptions. And these come in three varieties. So we have the no throw guarantee, which says, hey, I promise not to throw an exception, but if I ever do, panic, terminate me right now. All right, don't let me do anything else, kill me right now. All right, then you have the basic guarantee, which says that, look, when I come out of a function block with an exception, all right, there is no memory corruption, there's no leaking, and all class invariants will stay valid. All right? I don't know why that's an exception guarantee. That should be just a regular function guarantee. All right? It's not like, well, if there's no exceptions in there, go leak. All right? But they had to list it out because exceptions are so tricky. We need something to keep us safe at night when we use exceptions. All right? And then we have strong guarantee, which means that, look, when I come out with an exception, data has not changed. So it's got the same semantics as a database commit and then roll back. So that's exception safety. All right, so that is a brief romp through how exceptions work. Has anyone got any comments or words of, I don't know, attack? No? All right, it's early in the morning. I'll get you riled up further into the talk, okay? So the other way we can look at exceptions is the philosophy viewpoint, all right? What are the great thinkers of our time doing? The people that sit up on the mountain, all right, and send the tablets down. Here's what you should be thinking about exceptions. Right, we hear mutterings coming down of rare unhappy path events. All right, we hear in the wind something about non-trivial errors, serious things going on. So let's just delve into the philosophy of exceptions, right? And I do this with a series of questions, right? So this is my way of trying to get information out of the big thinkers. When is it appropriate to use an exception? Well, let's go to the guidelines. Runtime errors where a function cannot do what it's advertised. If a function can't do what it's saying it can do, throw an exception, all right? This is in the guidelines. This would have you throwing exceptions all over the place, which is exception, which is not the way to use exceptions. They're expensive for constructor operator failures, all right? It's the clean way of doing it. What about for undefined or unrecoverable system state? So I've got some sort of memory corruption, or I'm out of memory, I have memory exhaustion going on. Is this something for exceptions to handle? Now, you guys are intelligent. You're at this conference. You just have to put a thumbs up or thumbs down. All right? So you can't see it in YouTube land, but it's all thumbs down. You're right. All right? You shouldn't be using it for memory corruption and exhaustion, right? And Bjarne said in his D&E book, look, if you have a really complicated error handling mechanism that deals with everything, you've brought so much complexity into what you're doing that you've now given a source of errors. In other words, you've got diminishing or negative returns. It also means that people who walk up to me and say, but what about when you have memory exhaustion? I say, go away. I've talked about it here, all right? So this is not an argument for, hey, Pete, what you're doing, what about memory exhaustion? Because if I have memory exhaustion, I don't know if I can unroll the stack safely. I don't know if I can actually print anything out. I just know that it's time to stop. All right. So let me keep asking questions. All right, what are the use cases that exceptions were designed for? And this is not going up the mountain. This is me thinking about it, right? If a program has encountered a serious error, right, and going forward will do more damage than anything else I can do, then I want to get out of this control flow. All right, I want to terminate my program. I want to terminate this unit of work I'm doing. The second one is when we encounter a situation that cannot be dealt with properly because I don't have the context. I'm a lower level function and I don't know. All right, now, if you are that lower level functions calling the higher level functions and you own all that code, you can take care of this. If it's some third party, it's a lot trickier as they don't know what you're going to do with that, right? They just throw it and hope for the best. And that leads to a corrosive, what I call a corrosive effect on interface design. Instead of properly designing interfaces, people take the easy way out and throw an exception. And I say, if you're using exceptions for anything else, there's probably a better way. And we're going to go through that in this talk, all right? So question 2, are exceptions for very rare events only? I'll take a thumbs up or down. All right, I got a couple of thumbs down. All right, I'll come see you afterwards. All right. The guidelines say keep error handling separated from ordinary code. I assume that means stuff that's not directly to do with error handling. C++ implementations tend to be optimized based on the assumption that exceptions are rare. It's a very strange turn of phrase, being optimized because you're bad. It really should read, it's pessimized based on the fact you're not going to use it very often. Okay. And in the Microsoft guidelines, they say use exception handling if the event doesn't occur often. That is, if the event is truly exceptional, as one of these circular definitions again. Okay, saying like something, what does huge mean? It means it's like really huge, you know, it's like, doesn't really tell you much. But if that is the case, all right, how much of your flow, your data flow or your information flow to your system should be taking exception paths? What is an upper bound? 5%, 2%? Does anyone actually measure this? I say no. Now, SREs, at the very top where you're wiping transactions at the main level may well track that, but not tracking the local exception handling that will be buried in your code. And how do I handle frequent minor errors? So it's like first class. It's only if it's a first class rated error we can use exceptions. What do we do for all the little minor errors we have? Okay. And how can third parties know if it's a minor error? I use some third party code and I say, get me a file, and it says, this file is not here. How serious is that to me? Or I'm looking for something in the database and it's not there. Do I throw an exception? Well, it depends, right? I've seen where we have local error handling, which says, catch this thing. If it's a duplicate error, just like swallow it and ignore it, because duplicates are expected to be there every so often. And it's not a big deal. But a third-party library implementer will not know that, and that's one of the big problems I think we have with exceptions. There is a relationship there that's hidden. And finally, if you use exceptions for normal situations, how do you locate unusual or serious problems? Right. And I'll give a final word from the man himself, Bjarne, who said, and these are things I think if you don't really take anything else, this is something you should have in your head about exceptions. The assumptions were made on the design of bringing exceptions into the language. Exceptions are used primarily for error handling. They're not a separate return mechanism. You don't find stuff and throw it out in an exception and say, there you go. All right, it's purely for error handling. Exception handlers are rare compared to function definitions. What that means is most functions should not have try-catch blocks in them. All right? Otherwise, you got the clutter coming back. And the lastly is exceptions occur infrequently compared to function calls. So as you're calling function 1,000 times, you should be throwing exceptions 500 of those. Right? It should be very occasional. All right, and that comes from way back, and I think that was very clear thinking, which we may have lost to some degree. So my conclusion, as I went up the mountain, talked to people, come back down it, is exceptions are for functional recoverable errors, and there's one you can proceed safely, not for memory corruption or exhaustion. That's a different category of problem. And prefer to keep exceptions as rare as you can, meaning for serious or uncommon errors. All right. And that's my brief romp through the philosophy section. All right. I don't have that much time, so we'll have to move on. Anyone violently unhappy yet? That's a shame. All right. Let's keep moving on. I think I can do better. All right. So let's look at the usage-based view, which I say this is the defining characteristic of exceptions. Right? What are people doing with exceptions in real code? My follow-on question is, what should people be doing with exceptions in real code? Let's go look at that. This is the meat of the talk. So let's talk about exceptional resource management. All right, so what is the situation? I have explicitly got to give back or release a resource acquired during an operation before I leave the function with an exception being thrown, right? So exceptions can leave at any time, and I need to be able to clean up to keep that basic guarantee at least. So what's the pattern I'm looking for? The exception block catches the exception, releases a resource, and usually rethrows the exception. So how does that look? Now, here is a piece of code here that is actual production code. Yes, I know you think I went out of my way to make a particularly bad piece of code, but no. This is something that lives and breathes in production. You see here where it's let's release the resource. Now, this should be a clue. This is not error handling. It's resource management, right? But we do it here. Now, when I first looked at this, I was like, this is terrible, look at this thing. But then I said, there's a bug in the code that's hidden. We don't release the resource on the happy path. All right? Problems. Is there any way to get out of this problem? RAII, right, yes. Not well named, I prefer to think of constructor acquire, destructor release. So if I do a small file manager class, we say on the constructor I'm going to open the file, and on the destructor I'm going to close it. All right, my code goes from that big, long, windy thing you can't get your head around to something like this, a simple do-while loop. Now here I have one line in it because that's what would be in this actual file, but this could be 20, 30 lines, and if there's extra return statements, they'll all get taken care of. Now when I did this example, I hadn't gone and looked at design and evolution, but I found this in it. I was like, this is cool. All right? Bjarne almost did the exact same thing. So this is not new or something that I've discovered. Something from the very beginning, people said, do not do this. And yes, we do. All right, so what's my conclusion? Use RAII over catch handlers for resource management because it's not error handling. Let's move on. The exceptional trier. What do I mean there? What's the situation? I have a potentially temporary problem that retrying may solve. All right, so exceptions can be caught and used as a retry counting mechanism. No, you say that's too cool. No, you can't do it. Kind of messy, but some people will see it as neat. And the pattern is that the exception is in a loop and has a conditional rethrow. Now these rethrows, if you see a rethrow, it means you're probably not handling the error. You're doing something maybe nefarious and then putting the error handling someplace else. All right, so let's take a look at that beast. All right, so what do I have here? I have up here, look, conditional rethrow. If the retry count is greater. Anyone unhappy about that? Who likes this? Thumbs up, thumbs down? Come on, it's not that embarrassing, but your thumb. All right, has anyone got the thumbs up? Because I want to go after them. All right, you, out of my talk, all right? All right, conditional rethrow. Now, it can get even worse, right? If I have, in this case, I have to say, right, when I connect, I've got to do a notification somewhere. And now what happens is I start having a duplicate functionality in the try block, also in the catch block, right? And if it gets big enough, someone will put one in one place and not in the other, right? So what do we do here? Well, I say, just do something like this. Have a proper API. Stop letting the idea of an exception throwing frenzy you want to get into prevent you from doing it in a simple way. Return a loop variable, or return a success fail variable. Right? You aren't doing anything before with it, so it's not like you're going to push out some sort of pair of information. So when I say if the exception is in a loop and has a conditional rethrow, use a return status for loop control. Stop using exceptions for counting. They're supposed to be unusual. If you have it in a loop for like 20 times, right, when you can't find something, that doesn't sound like it's very rare. So don't do it. Anyone, any comments on that? These are the easy ones. I'll get you much more riled up later. All right, exceptional pass the buck. any problem whatsoever, be it so small, I'll throw an exception, because it's easy. Exceptions allow the thrower to offload the problem to the catcher. And I spent some time in Java, and I suffered the death of 1,000 exceptional cuts, because everybody goes, what? Something's not perfect, throw. Users generally need catch blocks throughout their code to mitigate, because if you don't, this thing will go right up to main, probably hit the swallower, and that piece of work gets canceled. And these are small problems that we mightn't even care about. All right? So we need local handling to mitigate this stuff. So the pattern is external libraries and modular functionality expresses all these problems through an exception. I could show you code, but it's just code with exception throws all over it, so you can imagine that. But I have some questions. Is having try-catch blocks all throughout your code base okay, even around multiple exception calls? Yes? No? All right, a lot of thumbs down. I like it. You're a very educated audience, meaning you agree with me. Okay? Is having an exception swallowers all throughout your code okay? No. There's thumbs down, you can't see it. Right? No, because you don't know what's going on in an exception swallower. It's completely mystery what's going on. So the answer is no, right? As you guys got right. Part of the benefit of exceptions is the lack of these constructs all throughout your code base. And that means that you should be thinking try-catch blocks are ugly. A straight swap of try-catch blocks for if statements is you're on the wrong track. And it's not efficient. We already talked about that. And again, how do you locate serious errors apart from calling your class really, really bad error or something like that, right? So one comment that was made, so when, I believe, I got this from D&E, when there was all this talk about bringing exceptions into the language, everybody was pretty much on board except for one guy called Doug McElroy, right? And he stated that the availability of exception handling would make systems less reliable because library implementers would not try to understand problems, they would just throw exceptions, right? And it says here, the last thing, only time will tell to what extent Doug's prediction will be true. It's about 30 years later. Do we know yet? Bjarne, do we know? Was it true? False? He says somewhere in the middle, very diplomatic. I say he's pretty true. Now, who was Doug? Doug could have been just some guy who walked in, handed Bjarne a cup of coffee, and walked out again after dropping that comment, right? Who was he? All right. Doug was the leader, I believe, headed the Bell Research Labs where Unix was created. All right. And Bjarne said that Doug's influence on the development of C and C++ cannot be overestimated. And any critical decision he made, he liked to run it by him, even if he went against him. He said that Doug had a knack for being right. Doug also did a bunch of things in Unix, and he invented macros, which I don't know if that's a good or bad thing. I don't like him in my code. But he was a big guy in computer science, all right? So he's someone to listen to. So what's my conclusion for pass the buck? Prefer to use exceptions only for unusual, rare, serious situations. Okay, anyone got problems with this? Good, now you're starting to think. All right, so what about exceptional logging? You see a lot of this. So the exception thrower is missing context. All right, he's in a lower level function. And they can be missing some vital context for error investigation, which you're going to put in your log file. All right. So what do we do with that? We log the error with extra information in the handler and rethrow. We put it in a log or cout. Right? Or we repackage the exception as a different type with extra data inside of it, and we throw that instead. Right? And one, we log the error really deep in the stack, and the other one, we log it up at the handler. So the second one has a little bit of an edge on it. This often leads to modes of thinking where we think just the content of a string even is an error type in and of itself, which I disagree with. We'll go into that later. But the pattern we're looking for is the logging and repackaging of exceptions in the handler and a rethrow for the actual handling error elsewhere. So what am I talking about here? All right, I don't know if get name from type throws, but if it does, he does not know what the key is. And if the transmit name throws, it only knows the name and doesn't know what generated. So I want to put this in my exception handling. Right now, some people will go, oh, Pete, let's do it the really fancy way, right? Why don't we do it this way? I'll put the extra logging or the extra information in the constructor. I'll pilfer the what that's going out. And when you call my what, it has the key, the type, and whatever's in the other exception. Now, there's a slight problem with this thing here in that, what do you think happens when we create a new exception type and throw it? Right? We deallocate the runtime error memory, and then we allocate the my exception memory, we copy stuff in. So again, you're making things more expensive. All right? Is there a way, is there any possible way in this language that we could avoid something like that and still have the logging at the error site? So I say yes. There is. I'm going to bring the radical concept of a mutable string. All right. So I have an exception class which has a mutable string in it, and I can start putting stuff in and send it back up to the call site. I believe boost exception has this in it, which I did not know at the time. Someone told me when I give this talk at CPP now, but it's like convergent evolution. And if some people go to me, oh, you have a string inside of the class? What happens if you're out of memory? What happens if we're out of memory? You're screwed anyway, all right? So it doesn't matter, all right? So what happens now is instead of new classes, just to bring information in, I say, look, give me my e.what. I'm not going to catch it as a const exception, and I got to format add key type, so keep all the drivel of how I format this someplace else, and I can just read this. I'm just going to add some information. Okay, pretty neat. So I say when you're missing extra context, use an exception type with mutable logging. And I don't believe the standard has that, which is one of my many beefs with the stud exception hierarchy, which we'll get into more later. Anyone, any problem with that? Yes? Yes, you're talking about allocating on the heap possibly. It's got a string optimization in it, right? So unless you do something really long. Yeah. But it's a maybe, not a for sure. All right, let's talk about exceptionally hard to find. So I'm searching for something. I'm looking something up, and I can't find it, and I go, it's a somewhat clean way to indicate a function has failed to uphold, as the guidelines say. So I can say, hey, you're looking for what? I can't find it. Exception. Deal with it. Take your code down if you don't. All right, so again, it's a bit of an offload. So what are the pattern here? The exception thrower is some sort of search function that returns an object when found and throws an exception when it's not. So right? This is what we have going on here. So here I have, and this is from real code. I had to simplify it. I'm not allowed to put the actual code up here, and I wouldn't fit it on the slide anyway. But we're looking for an order based on an ID. And we say, look, if we can't find it, throw an exception. I can't find it. Now, maybe this is a big deal. Maybe it's not. If I control the code base, I know how big a deal it is. Right? And then down here, I can do the exception handling. All right. Now, is there anything in the language may have come in after C++11 that would indicate I have or I don't have something? Optional. Yeah, of course, optional. What are people thinking? All right. Look. Now, I have to change the function signature. People go, oh. So what? I own the code base. All right. So, stud optional, I say go find an order. It goes up here. If I can't find, return a stud op. And then down here, I can say the order's not found. Exceptions are gone. Right. Now, in C++23, right, I can do things like this. I might have done it before with sort of coroutines in our own coroutine library. But we now have monadic functions, right, monadic continuations. So I'm going to find the order ID, or else, right, that's what your parents used to say to you, right, or else I am going to say order not found and return a null op. All right, so that's just a way of me showing it's not in Clang, it's only in GCC, at least it was when I did it. So what's my conclusion? Prefer to return an optional which indicates a found value if the stack return is shallow. All right, it might be problematic if you've got to send it up 10 layers up the stack, but if it's a shallow call like we just seen there, use an optional. Let's talk about exceptional data passing. Now we're getting into the good stuff, all right? We have a handler that needs to perform specific actions based on data at the throw site. So exceptions can transfer information up the stack to the handler. It's more expensive than traditional return, but it's easier to invoke. All right, I can transfer this information up. It's what we were designed, one of the design specs on exceptions. So the pattern I'm looking for, exception contains data used to perform handler actions as opposed to just a logging and reset, what I call pure exception handling, where you just log the error and say, let's bin something and go on. It's going to do something else. So what are we looking at here? And look at here, someone stuck a nugget of information inside of the exception. And down here, we're able to use it. So we log the error, here's what's going on. But I got to do some cleanup operations afterwards. So I take something out. All right. What do I say? Well, look, I say we have this thing called expected. So if we're trying to return a couple of things, why not just use the expected? So I'm going to return whatever the function is supposed to return as the message, but otherwise an exception, I'm going to return exception. Kind of funny because this is exceptionless, but I'm using exception classes. So I like the irony. All right, so down here, I'll say, okay, apply something to this data. I get a result. If it has a value, happy path. If it's not, log it and then do whatever you're going to do with the error. All right, there's no problem here. All right, anyone got a problem with this?
When did we get stood expected?
We got it, I believe, in 17 or 20. I know I used Cy Brand's version of it before it was in the standard, so that was a pretty decent one to use anyhow. Oh, 23? All right, I've been using it since 17, so I am uber cool, all right? That's why I'm here. All right, so let's talk about class design just a little, because we see here we have a bunch of exceptions, right? The first two have this, whatever this message thing is in it. The third one has a format code. The other one has an info. I've got this like explosion of classes, all right? Is there anything in the language that helps us with a class that's just got a couple of different data types inside of it? No, not enum. Not variant. Oh, come on. It's template, all right? Look at here. I have a template, a class which is templated on the data that's inside of it. If I asked you this question in any other context where you weren't blinded by the idea of exceptions, you would have said, what are you doing? This is crazy. Make it a single class and template it. So why can't we do that with exceptions? All right. Here we have the constructor, which just is the string of whatever data you want to put inside of it. We have the data coming back. I have a mutable form in case I need to catch it, put more context in it, send it on its way. All right. So what happens in my code? All that happens is it becomes just an alias. All right. Here's my exception back client, and down here I can just do the same thing I've been doing before. This prevents this explosion of classes which I keep seeing in the exception hierarchies. So what's my conclusion? If the stack return is shallow, prefer to return as expected type of success and data failure. All right. I'm going to have to just kick up the pace a little. Additionally, use a simple class template like you would anywhere else in the language for transferring data in an exception. All right, seems obvious now, does it not? All right, maybe not. All right, so what about exceptional control flow? All right, this is one that we say the handler needs to perform very different actions based on the failure that occurs, whatever happened. So depending on the exception type that's caught, do something particular, specific to clean up. It's frowned upon in theory, but the polymorphic catching of exceptions is almost designed to make this happen. Otherwise, we would just have catch, exception, E, and there's no other exception type, right? Because you can only do the one thing. So we do have this, and it's used, and I think it's not such a bad thing. The pattern we're looking for is many exception catch blocks in a single try, and potentially each has specific functionality. So what does that look like? It looks like this here. Who likes this exception catch hierarchy? Right? Now you might say, look, it's doing all the one thing. Why are you doing that? That's what people do, all right? Who hasn't seen this kind of thing, right? Somewhere in your head, you've got the idea that all these are different, but you're doing the exact same thing with them in the catch handler blocks. But be it as it may, I'm going to leave that as is. I'm going to say, what do I think we should be doing here? Well, I think we should have a variant of your exceptions, all right? And then my expected is just my happy path data, or the variant of what went wrong. Then that's pretty easy, right? We just applied the data, we get a result back, has a value, great, happy path, go do your thing. And if not, I'll just use this visit, right, generic lambda visit, where I say, whatever comes in, just log it and do this operation. and we'll return the error. All right. Kind of neat, but you said, Peter, you stacked the deck for yourself. That we're all doing the same thing. That's crazy. Yes, it is. And that's what I say in code reviews. Right? But here's what we have now. They're all doing something different. This is real control flow. Right? I'm doing a warning or an error or a handle. I'm doing something different. Can my paradigm handle this? Is this like the one that takes me down? No, I have a simple class. I've used it in other talks. All it is you give it a bunch of lambdas it inherits from, and you can use it in the visit pattern. And all we say is here, look, I create an overloaded. This is my variadic template. And it's going to give you, here's the lambdas to handle each of these. These will get pulled down in that class. And I just use the visit pattern here. All right. No exceptions. Neat. How's everybody about this? I brought up the boogeyman of control flow. Everyone okay? Yes? Going to do this Monday morning? All right. I hope so. So my conclusion is if the stack return is shallow, prefer expected with an error type that's a variant of your exception types. Now, if you have a variant with 500 pieces in it, right, your compiler is going to really choke, which is why you need to keep exception hierarchies down and not gratuitously inflate them. Let's talk about hierarchies. These things really tick me off, all right? I have lots of different error modes, and I want to use exception types to represent each and every one. For what's running in my head, I want that on the paper. Right? So exceptions can be many and varied, with the type indicating some kind of categorization of the problem. However, the real information is usually in the message, or the log that's in there. All right? So the pattern we're looking for is a single try block. You got many handlers doing the same thing, or a single catch handler for a parent class, even though we're throwing a bunch of derived classes. How does that look like? Looks like here. Anyone see a problem in this code? Shout it out. Come on. We're all friends here. All right. Problem is logic errors at the top. Now, people say you shouldn't be throwing logic errors in the first place, but logic errors at the top, and underflow and range inherit from it, so they would never get called. So I got to flip that around. All right, and that's an error that introduces when you have these 30 different catch handlers on a try statement. Usually it's some main processing loop. All right, so how would we solve this problem? What would we do? Anyone? Help me out here. All right, if I said polymorphism, would that help? All right, we catch by the base class. All right, why have we got all these handlers? We're not doing actual control flow. We're doing the same thing over and over again, so a single operation can handle it. That's what the catch handler should be doing. Have I solved the problem? No, I haven't. Because in my mind, I got to track down the clown who did this. All right. All these separate logic, underflow, range, runtime hours, and what am I doing at the catch handler site? Spitting out the message and then going on about my day. All right. The functionality that's in the catch handler is just a log and continue. So why do I have all this is just something that's running around inside your head. It's all different kind of stuff, right? But the message will be what's really, I'm looking, when I'm in a log file, exceptions to thrown, I look at what the exception message is. I don't see the type, so I don't believe I do. All right, so what would I do here? I would say, look, let's just throw the base class that we're catching. Anyone got an issue with this? Compiler's got an issue with this, right? It says there's no matching function for stud exception. It doesn't have a char star constructor, which is true. And one of the things that really gets me, right? I have a what function for prints in a string. And this is not a pure virtual class because you're not allowed to catch pure virtual classes, all right? So what do I do? What happens when I print the what on a only thing I can do a default constructed stud exception? What do I get? Implementation defined, something. All right, doesn't make much sense. I got to back it off to a runtime error. All right, but I have some. What? The advantage? Less exception classes. That's the advantage. Someone asked me, what's the advantage? I don't have a bunch of classes that do the same thing. But if I have a catch handler that's a parent class, why isn't the thrower not throwing the parent class? Assuming I control that stretch of code, it's in my code base. I understand One, if you're using a third-party library, they don't know that's a hidden relationship. Or if it's I'm doing different control flow, I'm doing something different. But outside of that, why are we doing it? And why are the derived classes at all if the no control flow has been used? Which is just what I said. So if the catch handler is performing the same operations for different exceptions, why not use a single exception class? All right, functionality rules. All right, now stud exception is no string constructor. Anyone know why? I didn't know why until I went to CPP Now and I said to the guys, I think it probably did the damage. Why? And I said, that's because if we're out of memory and we throw a bad alloc, we don't have to worry about string allocation. So for the point I said we don't handle in exceptions, and most everybody agrees with me, we've optimized the hierarchy for something that's an edge case we probably shouldn't even be handling. All right. And if I look at the exception hierarchy I have, runtime and logic error, what is the difference between these two? Okay, so I looked it up. One defines the type of objects thrown as exceptions, presumably detectable only when the program executes. Presumably, nothing hard there, like maybe. All right. What about logic error? What does logic error do? Well, it defines the type of objects thrown, blah, 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 presumably detectable before your program ran. All right? However, we only caught them at runtime, so how is it not a runtime error? All right. And what is the difference in functionality between these two classes? These classes are identical in every respect except for the name. Absolutely identical. We really wouldn't do that anywhere else in the language. All right? And when people see this kind of thing, they do silly stuff like this. All right. Now, without control flow, that's the exception. But with stuff like this, they pull all these it's just like, oh, a bad value, bad ID, empty set, whatever, one of the previous projects I worked in had something like 70 exception classes, and we didn't have that many errors, right? But it's just like, look, in my head, it's different. So anyway, getting back to this one, all right? So we need to go back to basics on this. I'm not on the back to basics track, but I will do a sidestep, all right? Let me talk about stuff and how it works in the real world. So Shakespeare said, a rose by any other name would smell as sweet, all right? Meaning the reference and the name of things do not affect what they really are, so, right? The girl there knows it's a rose because it smells and feels like a rose. If you tell her it's a Volkswagen Beetle, it's not. Right? But I'm a little too artsy there. Let's go to something more concrete, more scientific, the duck test. If anyone ever sees my tag here, it has if it walks like a duck, quacks like a duck, don't tell me it's not a duck. All right? So this here says that something can be identified by its characteristics no matter what you name it. And here there's a picture of it, well, it could be a rabbit in disguise, right? See that picture? Could be a rabbit in disguise. It's not, all right? Just for anyone who's curious, it's just a duck. So what do I say? I say prefer to throw a base class if the catch handler is for a base class and you control that span of the code. And additionally, prefer single exception types and catch handlers if the operations are the same inside of multiple catch handlers. All right, so that is a romp through the view, and I'm running a little low on time, so I'm going to carry on. So exceptionally unwindy, right? So one thing we get with the exception mechanisms is stack unwinding, which I think falls into 3 categories. Terminally fatal. Something has happened, usually in startup. I can't connect to a database. I can't connect to something vital. And that terminates my process. Now, I could terminate right down where the problem is, but that's bad manners, terminating someone else's code. So we send an exception up. The second one I call transactionally fatal. You're dealing with a unit of work. You've gotten into such problems you can't handle it. You say, I'm going to bin that, take another one, and the next one that's going to be a better day. All right? And the last one is local error handling. That's usually used to erase or mitigate or recover from exceptions. Lots of times because the guy throwing it is not the guy catching it. And we have to do things like swallow it or make it go away or log something and continue on. However, the thrower does not know that return depth. It's one of these hidden relationships. And it can be imposed by third parties, in which case you just have to live with it. You don't have it, right? But I think in that case, like we went through a lot of the examples, we should be handling this without exceptions when the return is shallow. So now we are on to what I call the truly exceptional. We've got rid of a lot. What is the gazing on the divine? All right. What do we have left? What should they be used for? I say error tracing and logging, right? And what makes a good logger? Why aren't we taking account of that? To me, what is the error? That's the dot what, we have it. Where in the code is the error? I want a dot where, right? So stud source location handles that. And I want a dot backtrace or dot stack trace and say, how did I get here? Okay. I also want it for stack unwinding. Exceptionally deep stack returns. I'm parsing something in the middle of a JSON parser. Something goes wrong. Throw me back up to the top. Take some other line or take some other thing. Right? So it's a way of getting out of a deep stack trace without having to like poison your whole stack coming back up. Right? And also for transactional and process termination. And also for control flow. Yes, I know we say it's not a good thing, but the real world needs it. So let's encapsulate control data. And without long, repetitive class hierarchies. Right. So this is what we should do. Now, you say, Peter, you've come here today, you've bellyached about the standard, talked about bad things going on. Well, yes, but I bring stuff, right? I am the alpha, I am the omega. Everyone will come to he who waits. Boom, we're going to have an exceptional exception class, and it looks like this. All right? The omega exception class. Right? Now, this is not one you say, push this into standard or something. This is something that can be easily and flexibly mutated to do all the jobs your current long exception hierarchy does. So what do we have? So we have the user data. We can pop that in. All right, we have the constructor. Really, that just puts a string in your data type. The rest is all done. All right? We have the mutable what. You want to stop, put stuff in, context, let it go. We have source location. Where am I in the code? I don't have to go, you look at exception, you go, you code, you grep and hope that the string is sufficiently unique to find it in your code. I might want to know how I got there. Give me a dot stack or dot stack trace on it. And again, we have the data. All right, we want to say, give me that data, maybe I need to mutate it. So this is the exceptional exception class. All right, does all things, should take care of most of your exceptions. This handles everything I've come across. I needed some utilities because it kind of sucks the way stack traces are printed, so I give my own. But this thing, you've seen it statically, you're looking at it, you say, wow, I'm not that impressed. Just like you see, panthers and cheetahs running along the plain, we need to see this thing in use, in motion. And what are we looking at? Well, look, I am creating exception classes with my exception class template. All right, boom, using aliases, easier, and gives you that grain, fine grain for control flow. When I want to throw it, here I just throw it with the string, and the piece of data, here it's an enum, could be anything. And in my catch, I just say, let me log this, failed with blah, 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 and look at what I get in my log file. All right, failed to process with a code, it's in this file, this line, and here's the function. Wouldn't this be nice? When you're looking down an error. All right, not impressed still, let me wow you even more. All right, look at this, I have a bucket of data, same exception class, boom, I'm gonna throw it, and then I catch it here and I just say, look, print out the data, the what, the stack, and I got some data in there to send my error on someplace else, and I get a message like this, failed to process bad order ID, and here's how we got here. All right, I predict if people start using this kind of methodology, people are going to be like, man, someone just threw a runtime error. Like, what the hell is that? I need all my information. I need to where it came from, where it happened. Stop making me grep through the code. So again, in conclusion, last slide, exceptions are defined by their catch handler usage, what you're doing with them, not what's running around in your head. What should they be used for? Error tracing and logging. Stack unwinding, reset or termination, deep stack returns. Data passing control flow when necessary. I'm not saying go out and figure a way to use it. If you need it, use it. And when should they be used? Well, they should be used as rarely as possible, right? For serious, infrequent, unexpected errors. And with as few exception types as possible, determined by catch functionality. And that should all be done, hopefully, with my Omega exception class. Plug. That is the end of my talk. I hope we change your thinking a little, or that you think of it a little differently when you do exception classes going forward. Thank you. If anyone's interested, here's other talks in the real world. All right, singletons, APIs, legacy systems. If you're interested in the Godbolt, it's all worked out in Godbolt. And I don't think we have time for questions, right? I think we're out of time. We have a minute or two? No? All right, go home. All right, so we are hiring. We have a booth out here. And if you're in YouTube land, we have a URL. So, Bjarne, we have to have time for you questions. Please.
I think I'm supposed to make a comment. At least you asked me yesterday.
I did browbeat Bjarne to come here to sort of give his perspective.
So it's really quite scary, somebody doing a really fine reading of a piece of rather difficult writing you did 30 years ago. With 30 years of experience and such. I think one of the problems with exceptions is that people want to use them with a lot of raw pointers. It was advised against at the time, but, well, thousands or hundreds of thousands of people did it and got into the predicted trouble. One thing that's worth mentioning was when I designed exceptions, I couldn't figure out how to solve this problem immediately, and it held back the design for about half a year till I realized how to use constructors and destructors, what eventually was called RAII. Sorry about the name, but I was very busy that year. The other thing is I'm not a fan of the standard class hierarchy.
That makes two of us.
Exception hierarchy. And I actually, at the time and still now, tend to invent classes to be thrown that doesn't...
You don't have to invent anymore, Bjarne. I've just given you the godlike Omega class.
I'm not going to comment on the later features. I'm going to stick to generalities.
I'll take that as a thumbs up.
At the time, this was about the height of the object-oriented rah, and we didn't yet have things like templates and lambdas.
Okay, thank you. Yeah, so we didn't have temp. And again, just in closing, right, the normal process you would use to design classes can be applied to exceptions. They're not some mythical thing where you turn your thinking off like you're in a dream, you know. So anyway, thank you again. And if anyone wants to come outside and, you know, take me down or talk about exceptions, I'm here all week. Bye now.